A lot of the things that we're going to be doing over the next couple weeks are sort of repeats of the stuff that we've done already. For example, today we're going to talk about rotational kinematics. And believe it or not, rotational kinematics is very similar to normal kinematics, the stuff that you've grown to love a long time ago. After kinematics, we're going to talk about rotational energy. We're going to talk about rotational momentum. We're going to talk about the rotational equivalent of forces. All right, so we're really going to be sort of repeating what we've done with just the additional twist of adding in some rotation. So really, there isn't anything all that new for the most part. All right, just a little bit of additional complexity. But really what we're going to be focusing on is the topic called rotation of rigid objects. Now, it's important that I state rigid because we aren't going to be dealing with things that react differently. I need to spell rigid correctly. So we're dealing with rigid objects, which is to say we're dealing with, things that aren't fluids, basically. We're not dealing with liquids, we're not dealing with gases, we're dealing with solid objects. In other words, we're dealing with objects that don't change their dimension depending on how you rotate them. Wheels and things like that. All right? So the rotation of rigid objects is governed by a set of physical principles, and we refer to those principles as rotational kinematics. We're going to start off talking about rotational kinematics. In other words, rotational motion. Now, I've already told you the equations of rotational kinematics are very, very similar to the equations that you saw for linear kinematics. The only thing we have to do is really introduce a new set of variables. All right, so we're going to start off doing that today, talking about the quantities, the rotational analogs to linear and translational quantities. But before we do that, I want to make one little note. We're going to be drawing a lot of circles for the next few weeks. There's an important quantity that relates the radius of a circle and the arc length that is subtended by some arc. All right, so we have a circle here of radius r, and I'm looking at some arc length, which is this length right here. We usually call that something like s. That is formed because we subtended some angle theta by these two lines. All right, so if I want to compare the arc length s to the radius r, what do I need to know? How can I do that? How is s and r related?
The length of the sector is proportional to theta multiplied by the radius.
The length of the what?
The radius. It's proportional to the radius times the angle.
Okay, so the length of the arc is proportional to r theta. That is absolutely true, as long as theta is measured in what? Radians. All right, so theta has to be measured in radians. And that, in a nutshell, is why we use radians, so that we can relate rotational quantities such as theta, such as an arc, to linear quantities such as arc length or the radius of a circle. Right? I switched over to a little r here. Sorry about that. That was actually, as I drew it, a big R. Okay. So as long as you measure theta in radians, then in this case, the arc length is exactly equal to the radius times theta. Right? And we're going to come back and use that in a little bit. Okay, so let's start to talk a little bit about some of these quantities that we want to use. So we've already introduced one quantity that we're going to become familiar with, that we're going to use when we're talking about rotational kinematics, and that is something called angular distance or angular displacement. All right, so the rotational analog to regular displacement is just angular displacement, and that gets the symbol theta. All right, and of course it's measured, as we just mentioned, in radians. All right, but the angular displacement is simply, or the angular distance is the angle subtended by an object as it moves along an arc. So as the object moves from point 1 here to point 2 over here, it subtends some angle theta. And that is the angular distance measured in radians. All right? So nothing really big there. So we'll move along to the next new quantity, which is angular velocity. Okay, now so we're dealing again with rigid objects. So rigid objects. Mathematically, what we're really saying when we refer to the fact that we're looking at rigid objects, or we're dealing with rigid objects, is that if we look at the position of some object from the axis of rotation, all right, so again, here's our circle, and we know that object, the red ball, is some distance r from the axis of rotation. All right. If this object is rigid, and we can certainly allow this ball to be rotating around the axis of rotation like so. But if this is a rigid object, how does this r value, the distance of the object from the axis of rotation, how does that change with time? The r is constant. All right, so in other words, dr dt, the derivative of r with respect to time, is 0 because r is constant. Okay, so mathematically, when we say that an object is rigid, that's what we're referring to. Now, that equation dr dt, that sort of looks like an equation for velocity that we've dealt with before. When we're talking about velocity in general, it's the derivative of position or displacement with respect to time. So that won't work for our definition of angular velocity. But certainly something is changing here, right? Because we can say that, well, at some time t equals 0 seconds, our object was at that point. At t equals 1 second, our object was at this point. So it has moved. So the quantity that's changing here, the quantity that represents position or change in position that's changed, is actually our angular distance or angular displacement. So if I subtract theta 2 minus theta 1, where we're defining theta from some coordinate system again, all right, which I haven't shown here. If I take the difference between my angular position, or in other words, if I take my angular distance divided by time, by the change in time, I get something called the angular velocity. All right? And in this case, as I've written this, it's the difference between two finite instances in time. This is really an average angular velocity. Where this W-looking thing is actually a lowercase omega. Sorry if that's not obvious. All right, so Greek letter omega, excuse me, is the character that we use to represent angular velocity or angular speed. Yeah, Joe.
T2 minus T1.
Thank you. T2 minus T1. That would make a lot more sense.
Yeah. Going by 0 side.
Indeed. All right, now let me just point out here that I haven't really defined my coordinate system properly, so I'm going to go back and I'm going to label my coordinate system. By convention, and this doesn't really matter, but by convention we tend to define this as theta equals 0. That line, the horizontal line, to be theta equals 0. Okay? And then we define positive theta counterclockwise from horizontal to the right from the axis of rotation. So this should be a little bit familiar because you should deal with when you're dealing with rotations in math class. Usually we start with theta equals 0 at that point. And I'm certainly free to say that this is actually like negative. That's a negative rotation going in the opposite in the clockwise direction. We usually stick a negative sign on the front of the number, and then like I said, positive is always clockwise. All right. So theta 1 here would be something like negative 45 degrees. This is theta 1, and then theta 2 would actually be this number. So my angular position would be different. Okay. It doesn't always really matter. Just like in any physics problem that you dealt with so far, you're free to choose a coordinate system as long as you solve the problem correctly. But a lot of the times in problems that you're trying to solve, we'll ask you for, okay, relative to, basically like the positive x-axis, what is the rotation or something like that. So that's just a convention that we use, but you don't always necessarily have to stick with it. All right, so you've seen this before. If we defined an average velocity using two discrete values, well, you can find an instantaneous angular velocity how?
Taking the limit as delta t goes to 0.
All right, taking the limit of this thing as delta t goes to 0, which then gives you a derivative. So we're taking the derivative of theta, the angular position with respect to time. All right. A quick aside on the units of this thing. So theta we've already talked about is measured in radians, which means that this has the units of radians per second. All right. Now, radians are sort of a funny unit. They're sort of not really a unit. Okay, so we include them when we're talking about, when we're talking about these quantities, but when we do any sort of unit conversion or math involving these quantities, a lot of the times the radians are sort of just ignored because they're not truly a unit. They're more like a ratio. Right? And you can see that if we take a look at that equation, that the first equation I put up there that related an arc length to the radius of the circle that the arc is forming. All right, S is an arc length. That's a length that's measured in meters. R is a length measured in meters. So theta really has to be unitless. I mean, yes, we call it radians, but it's sort of like a fake unit that doesn't really count. All right, theta is really just a ratio of the circumference of a circle to the radius of a circle, essentially. So radians are funny units. Which means they can just vanish magically when you're working with them in an equation. All right, let's keep up our breakneck speed and move on and talk about angular acceleration. Okay, so just like in the translational world where we have, if we have an object whose velocity is changing as a function of time, we can have an object that is rotating that has an angular velocity changing as a function of time. So in that case, the picture might look something like this, where the wheel is spinning with some omega 1 at t naught, something like that. A little bit later, the object speeds up and now is moving at some omega 2 at time sub 1. All right. So our angular acceleration then we can calculate, and we give the Greek letter alpha. It's simply the difference in the angular speed divided by the difference in time. Wow, I keep doing that. Keep trying to do zeros. I'm sorry. Omega 1, and this is just how I've written it for some reason. All right. So this is the average angular acceleration, which is simply the difference in angular speed divided by delta t. And if we want the instantaneous angular acceleration, we just take the derivative of omega with respect to time. All right, once again, we look at the units of this thing, and you see that we get something like radians per second, or radians per second squared. All right, so we're putting together a little bit of a picture here, and just let me summarize this in a nice table. And hopefully this is very obvious to you. That we have some some equations that are very, very similar between the translational world and the rotational world. So we have equations for distance, we have equations for speed, and equations for acceleration. In the translational world, we use the generic symbol x for translation. If we knew x, or delta x rather, if we knew how if x position changed with time, then we could calculate a speed, which is delta x divided by delta t. And if we knew how speed changed with time, we could calculate an acceleration, delta v over delta t. I'm giving you the average values here, of course. Replace deltas with derivatives to get the instantaneous values. In the rotational world, our distance traveled is something like a delta theta, so the change in angular position. If we want to know the angular speed, we take the change in position with respect to time, delta theta divided by delta t. And then if we want to know the angular acceleration, alpha, we take the change in angular speed with respect to time. All right, so our equations are, again, very, very similar. We're just swapping out a few variables. X's become thetas, V's become omegas, A's become alphas. All right, so like I said, there's not really all that much new here. Now, these quantities that I've been referring to here are all the scalar equivalent to the vector quantities that we've dealt with in the past. All right, I'm talking about distances, speeds, and accelerations. If I want to talk about displacements and velocities and accelerations, I really have to include a direction. Right? I need to assign some sort of a direction to my numbers so that they become vectors. So the question is, well, how do we do that? In the linear sense, in the translational sense, that's pretty easy. We say, well, objects could be moving up, or they could be moving to the right, or maybe down and to the left, something like that. It's always obvious what direction the objects are moving, and even it's obvious which direction the objects are accelerating. But in the rotational sense, things are a little bit more complicated, because now we have things that are rotating about some axis, and at one point in time maybe they're moving in this direction, but you go to it a little bit later. The speed hasn't changed. Maybe the object isn't accelerating, but now the object is moving in a completely different direction. So how do we assign a direction to an object that, for all intents and purposes, is really moving in one direction? It just happens that the physical direction seems to be changing. So you could just say that this object is actually moving at some omega 1, and that omega doesn't change. It's not accelerating or anything. Nothing funny is going on here. But the direction of the object is certainly changing. So in this case, what do you think? How would I assign a direction for, in this example, omega? What is the direction of omega? What would make sense? Up, down? Counterclockwise seems to be pretty reasonable, right? I mean, because the one thing on these two pictures that isn't changing is this little half semicircle thing. So that's one way to look at it. We could assign it counterclockwise, and that's sort of what we do. But what actually really happens is we do assign a direction. In this case, we say the direction of the angular speed is out of the board. All right? So if you think about the axis of rotation of this object, what axis is this object moving around? Right? It's rotating around some point in the middle of this circle. We try to draw this sort of in a three-dimensional sense. So here's the same object. Now we're just sort of looking at it more edge-on. The object is rotating that direction at that point, and then once it gets over here, it's coming around like so. So the object is orbiting around this axis of rotation. So what we define as the direction is always perpendicular to the motion. So the direction that we assign to this motion is perpendicular to the plane of rotation, the plane of orbit, if you want to think of it like that. And in this case, it's going to be pointing up. So this is the direction of omega, is up. Now the reason that we do that is because that allows us to use something called the right-hand rule to assign a direction. So we use the right-hand rule. All right, the way that the right-hand rule works is you have to use your right hand, believe it or not. And what you do is you take your fingers and you point them in the direction that the particle is actually moving, the object is actually moving. So in this case, this object is moving up here, and it's curving around like so. And the direction that my thumb points is the direction that we assign to the motion. In this case, the angular speed is pointing out of the board. All right, so I point my fingers in the direction of curvature. My thumb gives me the direction of motion. All right, that's called the right-hand rule, and it allows us to assign direction to things like displacement, things like velocity, etc. All right, everybody do this with me. Now be careful because many of you are right-handed, so you're writing with your pen, which means that your free hand is your left hand. I actually had a friend do this, senior level physics back in college, working on an exam. He's doing the right-hand rule. He's like, I keep getting the wrong sign. And we're like, well, your math's all right. Everything looks good. He's like, and so he's showing us, and he's writing. I'm like, wait a second. Greg, you're writing with your right hand. You're doing the right-hand rule with your left. If you do that, you get the wrong sign. All right, so everybody do this with your right hand. The curvature is up and then curving to the left. So our fingers want to curve naturally that way. Our thumb should stick out of the board. All right? In this case, we're sort of looking at the object going into the board here. So my fingers go into the board and then coming around and out of the board. My thumb is pointing upwards. All right, so this is my pathetic attempt to do a 3D drawing on a 2D canvas. I think it's pretty good. All right, so into the board here, out of the board on the left-hand side, thumb points straight up. All right, so that gives you the direction. So what you're going to start seeing now is when I assign a direction to omega here, what letter will I give it, or what unit vector? If I say that, let's just say that this object is moving with some angular speed omega naught. So I want to write my omega vector as omega naught with some direction. What unit vector will I assign? Right? If I tell you that, let's say that's the x direction. The y direction is into the board, and then this is z. So this is x, y, z. All right, so what unit vector do I assign to omega naught? Haven't used unit vectors in a while. K hat. Good. All right, so my omega vector is going to be given some value, which I just call omega naught, some number, and then the direction is k hat in this case. So you're going to start seeing, a third dimension pop up in your math. Even though what we're really doing is we're working in 2 dimensions here, right? The particle is moving up and down, left and right. It's not moving in 3 dimensions. But the unit vector does represent that third direction. Right, so there's a little bit of extra complexity here. Now, the reason that we do it like this is so that we can say, first of all, we can actually say, okay, yes, the object is really just moving in sort of 1 dimension. It's moving counterclockwise, right? But we're going to actually, when we do actually have to work with vector quantities, when we're dealing with, different physical equations where you need to keep track of those vectors, it's important to know to be able to assign a direction to this motion. Right? It's important to realize that, yeah, we assign a k hat to this particular case, or something like that.